Hey everyone, so today we're going to be going through the NVIDIA Deep Learning Institute, and we're going to be learning some of the foundations, robotics foundations for Isaac Sim and Isaac Lab. Let's go ahead and go to the website here, and I'll link the link below. So they have this training path for you already. We have these robotics foundation, and also before we get to that, if you just search the Deep Learning Institute from NVIDIA, you'll see a page something like this. Let's go to main page, right? You have something like this. You can browse the learning path, right? And if you're interested, you search robotics. I spelled it. Search robotics. It actually lays out the course for you, which is quite nice if you're a little bit confused on what order to take. And then there's simulations model. There's just a ton that you can have to learn and pick it up later on. But this is pretty good. I still recommend going through this one. It's already laid out for you. I think one more thing you can look at. Oh, that's the same thing. There's instructor-led courses. I think they're videos. Some of them are free, some of them are paid. But I think the free one are sufficient. And so we're gonna go through the robotics foundation for learning Isaac Sim, Isaac Ross, and Isaac Lab. This is developed by the NVIDIA folks. And let's go through really quick. So you have a beginner's guide to autonomous robots, an introduction to AI-based developed robot with Isaac Ross, and then you go through some of the Isaac Sim stuff, which is pretty fundamental. I've already gone through all of them. With the Isaac Lab, there's still parts of it that's coming soon, but don't worry, I'll tell you where to go from and how to go do about these ones. But we'll be going over that as well as part of this series. And so let's go ahead and start beginnings with the beginnings of autonomous robots. And by the way, I think you need to log in and you'll see this green button that would say start enroll. And you just have to click continue learning or start learning because since I've already learned. Now, I won't be showing all of these stuff here. I would just share what I learned from some of these, and I highly recommend you to go through these course yourself so you can have more in-depth learning. I would just be more summarizing them for now. Once we get to Isaac Sim, I'll do more of a hands-on teaching with demos. So for any given autonomous robots, you have the perception stack and cognition and action, and you interact with the world and you get some feedback, and then you do that again. That's how general a robot would do. Now, for what NVIDIA has been doing is the embodied AI. The embodied AI uses artificial intelligence and to kind of train in a simulation and to become able to interact with the physical world. So you can run your AI in simulation, train that, and put it in a physical robot. It's trained in simulation, and so a simulation represents a real world. And once you put it in a physical robot, oh, I have a body now. Interact with the world. It's kind of like Age of Ultron from Marvel's movie, if you know that. And one of the core part for embodied AI is the autonomous navigation, right? And then you have object manipulation. So how do you grab stuff? And we're going to be going over that. So the robot that kind of combines both would be a humanoid robot that's very popular right now, as you've probably seen around. And the human robot has requirement for natural language processing, and it needs to be able to collaborate with human. That's important. We don't want robots to punch people around or take some of stuff randomly or do something random. A collaborative robot is quite important for that. And in order to integrate your robot, there's several ways of pipeline to work with. One of the most cost-effective upfront thing to do is do it in simulation and test it rigorously, and then you transfer it to physical world. The reason is because all the physical parts are very expensive, and sometimes you just want to prototype the algorithm and see if it works. And so it's been a challenge to simulate that physical environment correctly that represents our physical world, so it can translate well. There's a gap between what we call the sim to real, so simulation to real. There's always that gap in between that, and it's turns out to be really hard to model some of the physical world entities, so soft materials, dynamics, and all that. But for working in Isaac Sim, Isaac Lab, you have several things. You have this thing called hardware in the loop testing, and you have software in the loop testing. So software in the loop testing, and we'll cover what these are later on. But right now I'm just throwing terms at you as well. And one of the framework that people often utilize is the ROS framework, so the robot operating system. It's not really operating system. I think we always need to clarify that. It's a middleware that transfers data and handles the network for you. But it also has a lot of robotics package that you can just utilize off the bat without writing your own. And so NVIDIA has already integrated that called the Isaac ROS. It enables you to have a better experience utilizing ROS and a faster speed. They tinkered a little bit with GPU. And for a typical hardware integration for robots, you have cameras for visual input, you have LiDAR, and LiDAR measures distance. And you have IMU, it's an initial measurement unit. It's how your phone knows it's upside down and knows how to rotate. And you have GPS that takes satellite signals and it tracks where you are on Earth. And for some robots, they have actuators. Actuators are like motors, so DC motors, stepper motors, and you have servos. So servos has more position control, where a DC motor, it just spins around without even knowing how much it has spun. And you also have pneumatics and hydraulic actuators for force applications, stronger grip, right? You can use a pneumatic one or hydraulic actuators, like a robot arm. And then you have the controllers. These controllers control the actuators, and or it gets data from the sensors. So you have microcontrollers like Arduino, and you have a single board computer. So the computers are more high level task and algorithms. So like Raspberry Pi and Jetson or Nano. You have an embedded system for integrating control solutions. So it's kind of a sitting in between of that layer of microcontroller and single board computers. Now, when it comes to autonomy software architecture, there is several blocks that NVIDIA was showing. So we covered the sensors, we covered the hardware stuff, the perceptions, and normally the first thing you do is you take input from all your sensors. So think of it as your eyes, your nose, your ears. So you're hearing, you're seeing data. The data goes in, and you try to be aware, you map out the environment around, and you also try to call delocalization. So when you first look at it, it's like, where am I based on what I understand? You could be your own coordinate reference. So starting at the beginning, 0, 0. And then you go through your perceptions again and you see, and then you get that feedback loop. And so let's say if I go to my living room or my kitchen, I update my information with that. Oh, I have a kitchen on my left side. I have my living room on my right side. Kind of cool when you're traveling. It's the same thing. You're kind of building that intuition in an unknown environment. You're building that map, and you're also trying to constantly ask yourself, where am I in that country or in that space? And so what we could build on top of this localization navigation stack is we implement simulations into it. We So the robot is still living in a virtual environment. We give that simulated environment and have it interact with that simulation. I think one of the NVIDIA folks, if you've watched anime before, the Sword Art Online is like you're in that simulation, or Ready Player One. I think that's a great analogy if you haven't seen those movies. So you put that robot in the simulation, it starts learning and to interact with that world virtually. And then so once you have these two stacks, you have the localization, perception, navigation stack, and then you have a simulation combined together, you can do some planning, so higher level planning. One of them is called the global planning. So how do you get to different waypoints, different coordinates, without hitting a block or getting tripped over or even go over blocks like that? And then you have a behavior planning. So what kind of behavior do I need to do to perform these kind of things. So does my arm need to move it here? I need to balance myself. And then you have a local planning, which is like a shorter path of things you need to decide. Let's say if I go from A to B is the global planning, and then in between those segments, at each segment is like how do I avoid these obstacles and what's the optimal path. It's kind of a minimum version of global planning. And so all of these with each other to get feedback. Perception stack, navigation stack interacts with simulation, and it interacts with your planning segment. And so all of these three components interacts with each other as well. Okay, let's cover the sensing part, which what we were originally talking in the first block. You have different types of perception, sensing, so cameras and LiDAR. For cameras, there is a ton of selections. We have monocular, a single eye camera. It's kind of good for capturing 2D images. So kind of imagine when you just use one eye, you're very good at, you can perceive it, but sometimes you're very hard to grasp the depth and distance. But of course, our human have a better understanding nowadays. So even with one eye, you can catch a ball through the shape and sizes of the item. And then you have stereo camera. So very similar to our eyes, two eyes gives depth perception through something called a parallax. And you have RGBD camera. So these depth camera has RGB camera with kind of what we call the ITOF. So it's kind of like LiDAR, but they sense distance at a closer distance as well. What's important is they give a colored depth data. And then you have thermal cameras. So Flare is one of the common brand. You firefighters use them to see fire, to see if there's people lying down or passed out. The thermal camera is very good to see through smoke and fog. It's not influenced by it due to its wavelength. And then you kind of a very futuristic, but not futuristic, what we call the event-based camera. It's really cool. I've seen it at an Automate show. Um, what it does is it detects movements, high-speed movements. And so if your camera is steady and I move around, it'll detect your edges and corners, and it'll tell you, okay, moving this way and that way. And what's cool about this is it's not subject to motion blur. I'm not sure exactly how the technical detail it is. I'll do some more research, but this would be very cool for kind of speed tracking. So if you put it on drone, right? If you use regular camera, you get motion blur or shaking of the camera. But with the event-based camera, if you just put it on drone, you shake it around, it still tracks very well. And you have the LiDAR, 2D LiDAR, it scans around, shoots some lasers and detects the distance on 2D and 3D at the same time. Not in the same time, but for 3D, it shoots up and down and then rotates. And you have these solid state ones. I think one of the brands you would know is by Livox. The Livox has some solid state LiDAR. They are pretty good. My understanding is the solid state LiDAR don't have a internal spinning laser. I forgot how they're utilized. I'll have to read about it more. And then what else? So other sensors are included with the ultrasonic sensors. You have radar, GPS. We mentioned that before. IMU, wheel encoders. Wheel encoders is something that measures your wheel spinning rate. Magnetic sensor. So these are more like a compass. It measures the Earth magnetic field, and that's kind of useful in a large settings in outdoor. Indoor, you're kind of subject to different magnetic fields. I think for drones and missiles, they actually use magnetic sensors encoded, so they know at which region of the Earth it is. And there's also touch sensors. So how when a robot is trying to grab, how it doesn't know that the temperature of it, the pressure of it. Looking at these lower kind of environmental sensors, so it measures temperature, humidity, and air quality. So what can you do with the perception stack? Well, one of the first thing you would do is what we call the sensor fusion. You combine what you see with other data. For example, your eyes perceive the environment, and I know my head is tilted this way because I'm looking at stuff in a different angle. And you also, let's say you combine with IMU, and so for your human body, there's something called vestibular fluid, and it's tilt even when you close your eyes as well. So you're kind of combining that. I have a visual confirmation that my head is tilting, and I also have an internal sensing. And let's say I am you, and say I am tilted. So you combine that data to give you more confidence of what you're perceiving or understanding in the environment. With the perception stack, you can do the very standard object detection and recognitions. You can recognize my face. I can recognize the dog. You can do that. You can track where they are and how fast they're going. Or a high level is called the scene understanding. Now, if you just, for example, if you give an image to ChatGPT, it'll say, okay, I've seen a dog in there and there's a box. There's some lights on top. It can describe what it's seeing. And that's really powerful for autonomous vehicles or even just any autonomous robots. And something that might not be well known to the public is that you can do something called visual odometry. A visual odometry takes a sequence of images and it tries to estimate how it is moving, how the camera is moving. And some of the good application is you can use camera alone or maybe combined with IMU to do indoor tracking. With indoor, you don't get GPS signal as well. So you can use a camera and then go around and it will know that you turn left here, you walk through the hallway. And so that's something called the visual odometry. Very powerful stuff in autonomous vehicles or mobile robots. And that kind of builds on top. That's kind of a foundation for SLAM. So SLAM stands for simultaneous localization and mapping. So you're constantly localizing yourself and you're mapping the environment as well. And I think I have a video I can share. Somebody explained it really well with using Minecraft analogy. I have to find that link again. And in terms of visual odometry, using camera to understand where you are, what we call the pose of the camera. You can also use LiDAR to do the same thing, but the algorithm is a little bit different. Usually LiDAR, you use something called ICP, iterative closest point, to understand how your LiDAR has moved. And for LiDAR, it would be called LiDAR odometry. And then the mapping technique kind of hand in hand with your localization or your odometry. And this is often what we describe as a chicken or the egg problem is how do you estimate your self environment if you don't know that environment? And so at the same time you have to try to map the environment. And so yeah, there's that. Okay, then you go back to the navigation and path planning, right? So the very standard A-star algorithm, what else? Dexter, RRT, rapidly exploring random tree. So these are the algorithms that tells you what's the best path with some rewards and punishment, and it'll plan out in a grid-like map structure. That's why map is important. You can tell the robot to kind of the path ahead of time using these algorithms and make those decisions based on that. And then we cover a little bit on the control system. So the standard control for that has feedback is what we call the PID, proportional integral derivative controller. And it's very good at putting your robot into a position or rotating a robot or controlling the motor at a certain very precise speed. And then for trajectory tracking, you have something called the MPC, Model Predictive Control. It is a little bit more sophisticated than PID control. I don't remember a whole lot about MPC, but they come with kind of predictive behavior to understand your robot's path or to optimize your robot's path as it navigates. And so one of the cool thing you would do in racing faster speed is you would use NPC to follow a line or follow a wall, or even try to follow an optimum path for racing. Okay, so we kind of covered more on the subset of what makes an embodied AI, which is the enabling the autonomous robot, right? We talk about the sensors, what it's used, its application. We talk about the perceptions, and a little bit on sensor fusion, how to combine these sensors, and we try to learn to understand what is localization and mapping. We outline the navigation part and path planning, and we also do a little bit on touch on control systems, so the PID and MPC. All of these are kind of huge course, would be worth a semester of course on its own. So there is a lot of things jam-packed together. But we'll try to cover this as we go with this course as well. All right, on to kind of the current trend in robotics, which is you've probably heard more on AI and reinforcement learning. Key areas that the NVIDIA pointed out is the robot policy learning. So these are different policy. How do you train them to pick up a box without really doing more sophisticated control? Like you have to pinch this, you have to do this. You just kind of put it into a reinforcement learning model with statistics, and you reward it if it gets closer to the box and even touches the box, and ultimately you kind of a little hint. I will learn that picking up a box gets the best reward, and so that's how your model is trained. And you have these kind of high level understanding is for the robot to understand. Okay, there's a box here, there's a bin there. I should put my box in that bin. You can also do large language models, so like ChatGPT. How do you program that into your robot? And then this is cool. The NVIDIA goes back to sharing a physical AI. It looks like there's kind of an interuse of embodied AI and physical AI. I'm not sure what the difference is. I just know embodied AI is more on the software side. You can implement software, where physical AI requires that you put in a physical body of a robot. But it seems like they terms a lot. But the Voyager, that one's pretty cool. You had something, and this is the Mind Dojo. So I believe they use Minecraft to train an agent to go through all the Minecraft tasks, which is really cool. Maybe this will be a separate video on its own. I like to explore this mind clip. Yeah, if you have time to explore this, I'm going to explore this. This is really cool. And you have the Voyager, same thing. It understands using, large language. Wow. That is actually my first time seeing this too. That is incredible. I will probably have a video covering this as well. That is really cool. Okay, go back to the training. And so something that popped up recently is called the NVIDIA Cosmos. Cosmos is what we call the World Foundation Model. And what that would do is kind of create a physical aware videos of a world state. So it's a generated live video feedback that integrates with your simulation, your robot simulation. It's a simulated camera that would show how your robot interacts with the world based on kind of more realistic physics. And what NVIDIA as example is they pick up, looks like they pick up a wheel and they give a visual feedback using Cosmo. And so the NVIDIA team has been trying to also create the mobility foundational model, which is a model that is trained for a brain. Essentially, think of a trained, well-behaved brain that can that can navigate around terrains with the action policies for autonomous vehicles. I think a key highlight for what these called the foundational model, which I just learned recently, is that these foundational model are kind of a breakthrough, or think of a basic standard that all the embodied AI should have. For example, the ability to navigate through path, the ability to avoid obstacles. And that's kind of like the basics of any robot should be able to do. And that would be implemented for a foundational model as well, trained in reinforcement learning in a virtual environment. And the goal for these is to have a zero-shot deployment. A zero-shot means that everything is trained in virtual world, and you don't need additional training in the physical world. Which I believe it kind of says they bridge the sim to real gap. That's kind of my understanding. And then what NVIDIA is trying to do is what we call the cross-embodied capability. This is something I interviewed with Tyler Ham, who's a PhD student. You can check out on some of our commentary. But a cross-embodiment is something you can transfer to other types of robot. For example, your autonomous mobile robot, it trains how to avoid, how to navigate. You transfer that knowledge to your quadruped, to your drone, to your humanoid, or something even more crazy robots in the future. Now, on top of that, we would be doing something called a vision language model, which is, or the large language model is something that combines with visual, is you tell a robot, say, hey, can you take me to the kitchen? And it understand that the user wants the robot to take him to the kitchen, and it tries to take its memory and understand where the kitchen is. It will navigate through and recognize based on its camera to know that the kitchen is already here. And so it's really become more human-like. You seen Waymo recently? I think I haven't taken one. I would love to take one. Is that something you can just you can visually tell like take me to this place or something? Or you can use an app. Maybe Zoox does that. I'm not sure. The speech recognition is part of it as well to understand what a kind of semantic reasoning with that. So all of these sounds very promising, but there's still huge gap for this, right? So the reason why we want to train a simulation is something that's generative is that because collecting data in the physical world is very hard. Just thinking about a driving scenario in the physical world, accidents don't happen every day. Well, it does happen every day, but not to the same person every day. So, but you need to get that all data so that robot has covered this scenario over and over again. And so it's kind of like the Matrix movie thing where you kind of virtual environment to understand different scenarios, how to do kung fu, how to fight, and all that. So that has been part of the challenge too. How do you bridge that data gap? And that is through synthetic generation, or you do it in a virtual environment with kind of randomized environment as well. And trying to do it real time is still pretty challenging as well. The competition of small devices has been really good so I'm pretty excited using Jetson AI, sorry, Jetson RN Nano to do that. And then NVIDIA is coining the term to make it more generalized, a robot to be more a generalist. A generalist for robotics would look like, oh, it can handle a very wide variety of tasks. So I can grab stuff, I can move this, put there, I can tell the robot to go here and there. Very good at everything and not really like highly specialized. And what's good with generalized robotics is that they can work well in human environment. We humans build tools for humans, for our hands, right? So if a robot can understand how to grab and use a tool, it has become a very good generalist, and it can integrate to a human working environment very well and collaborate with humans. So that's kind of the goal. And of course, there's just safety consideration. How do you collaborate with humans in a safe environment? So that's something you can test upfront in software simulation. Okay, so I think that pretty much covered the first chapter of learning the foundational robot. Again, in the next coming videos, we'll start diving into Isaac Sim. I'll show you how to go through some of these tutorials. You're more than welcome, and in fact, I highly encourage you to go through these courses yourself. Some of them are a little bit outdated, just because we recently have an update from Isaac Sim from 4.20 to 4.50. The UI looks a little bit different. I would say you can still go ahead and try it out, struggle it a little bit so you can learn. But if not, you can feel free to follow the tutorial in the upcoming future. So thanks again, and I'll see you soon.